Hey everybody. Um, Today we are going to be talking about section 5.4. And section 5.4 is one of the last sections in our last unit. It deals with the properties and applications of logarithms. So there are several different properties that we're going to discuss and apply today. The first three are the product, quotient, and power rule. So the product rule basically says that if you have a logarithm of a product, you're allowed to split that product up into the sum of the log of its factors. So you can kind of divide this thing up into its factors and expand it out as long as each one of them gets its own logarithm and there's addition separating the terms. The quotient rule says something similar. It says if you have a quotient, you can split the quotient up by the numerator and denominator as long as each one gets its own logarithm and subtraction separates them. And for the power rule, it says that if you have a log of something raised to an exponent, the exponent is allowed to drop down into the front of the log expression and act as a coefficient. And this is going to come in handy when we do some equation solving in section 5.5. So this one we're going to see again later. The other ones maybe not as much, other than creating a single log form so that it simplifies our equations. There are some other log properties that are just basic log properties. The first one here is that the log of 10 is 1, and that's because the base of every common log is 10. Similarly, the natural log of e is 1, and that's because natural log is log base e. Then we have log base a of a. When the base and this value here or variable here match each other, basically all of it cancels out and you're left with the exponent. In this situation, the exponent is 1. This is an expansion on that rule where your exponent is whatever it is and you have just the exponent left. And then the last one is where you have an exponential that contains a logarithm, and the exponential power has the same log base as the base of the original exponential, which seems weird, and it kind of is, but all of this is going to end up canceling out the base of the exponential and the log in the base, and you're left with just whatever else is in the exponent. So these are very particular ones that happen in certain scenarios where you have matching logs and bases here, but it just kind of depends on the question. All of these can be used to simplify expressions, and at times that's going to be very helpful, especially in the equation solving. So we are going to be using these different log properties in a couple different ways. The first one is to expand the logarithms out so that we can simplify each one of these expressions. And then any numbers involved, we're going to simplify as much as possible, again, without the use of a calculator, because we won't need a calculator with the way that these things are written. So the first one I want to take a look at here is log base 5 of 125x cubed. Now, 125x cubed is a product. We're going to split this product up as the coefficient and the variable separate. And since it is a product, we're going to use addition to do that. So each piece of this product is going to get its own base 5 and addition in the middle. Log base 5 of 125 plus log base 5 of x cubed. Now, once it's split up, each one of these logs can be simplified further. We get really lucky with the 125 because 125 can be written as an exponential expression with a base of 5. So anytime you can rewrite using the log base, you want to do that. Log base 5 of 125 is the same thing as 5 cubed. Plus, on the other side, we have a log of an exponential expression. So we're going to take this exponential and drop it, exponential, I don't know why I said that, exponent, and drop it down to the front like a coefficient because that's what the rule says. Any exponents can come down to the front as the coefficient. So we're going to look at 3 log base 5 of x. Now, there's a teeny bit more that we can do only because this thing right here has a matching log base and exponential base, just like in this property here. Log base and exponential base match. And what it does is cancels all of that out, leaving me just with the exponent. And that means that this whole first term becomes a 3. And then plus 3 log base 5 of x. And that is simplest form because that's as far as we can simplify this thing. Now, this second example that we have here does not simplify in this form. According to our rules, we can only expand out products, quotients, and powers. We do not have a product here, or a quotient, or a power yet. This is a binomial. It's addition in the middle. You don't split addition up with addition. You can only split up products with addition. So what we're going to do to create a product is factor out the common factor from this expression. And the common factor for each one of these is 9. So it's going to look like log base 3 of 9 times x plus 3y. Now this is a product, 9 times this binomial, which means that I'm going to be able to split this product up using addition. That means we've got log base 3 of 9 plus log base 3 of x plus 3y. Now again, that x plus 3y is already in simplest form. We can't do anything with it. It does not fall under any of our rules. But the beginning of this is similar to the beginning of number 1. We've got a log base and a value that can be rewritten using that log base. And when we can do that, we want to do that because it helps us simplify. So I'm going to rewrite my 9 again using powers because 9 happens to be a power of 3. So this 9 is going to become log base 3 of 3 squared plus log base 3 of x plus 3y. Again, that part's not going to change. And then in this last little bit, we're going to do the same rule that we did the last time and cancel out this log base and exponent base, leaving me with just 2. And then on the other side, log base 3 of x plus 3y. So it's going to be pretty typical that if you have a number involved, it will be able to be rewritten using the log base. That doesn't mean it always happens that way. It just means that if we're going to be simplifying, that's probably something that you should look at. All right. Now we have a couple more examples here. Number 3 has log of a log. And so that means we're going to kind of have to start from the inside and work our way out. So this piece first is the log of a product, which means we can take this log of the product and split it apart. This log is going to remain on the outside. So I'm going to put it on the outside with a bracket so that I can kind of organize all of my stuff on the inside. When I split this logarithm here, each piece of this product is going to get its own regular log 100, and addition in the middle, because it's a product, log x cubed. Now, because this is a common log, it's understood that the base of all these logs is 10. You don't have to put it on here. I'm just putting it on here for a second so you can see it, because it makes it a little bit more clear that we want to rewrite this 100 as the power of 10. Instead of having log of 100, we want log of 10 squared. Plus, in the other one, we're not going to rewrite anything, but we are going to take this power and drop it down to the front. 3 log x. Now, in a similar fashion to the other two that we did, the common log and the 10 are going to cancel each other out, leaving me with just 2 in the front. This piece is already as simple as it's going to get, 3 log x. Now, there's no way to factor anything out here that's going to make this thing able to be simplified further. There are no common factors, so there's no way to create a product. So this is simplest form here. This number 4 example has quite a bit going on in it because of the fact that it has a 4th root involved and all kinds of powers and stuff underneath. So when I have something that has a radical in it, instead of leaving it as a radical, I am going to rewrite every single one of these using rational exponents. Rational exponents are where you take the power attached to the variable and create a fraction with the root index as the denominator. So I'm going to set each one of these up like that first, just so I can kind of simplify this a little bit. So this is log base A. On top, I have m to the 8 over 4, n to the 12 over 4. On the bottom, a to the 3 over 4, b to the 5 over 4. Now, a couple of these are going to look way better because they actually simplify all the way. So if you get some integers there, like m and n will be, let's go ahead and handle that. Log base A. On top, I have m to the second, n cubed. But on the bottom, I'm going to have some fractions still, and that's okay. A to the 3/4, b to the 5/4. Now, it's important to note that when you have multiple pieces in the top and the bottom, anything that is coming from the top is going to be separated with addition. Anything that comes from the bottom is going to be separated with subtraction. Both of these pieces in the bottom are part of a quotient. So since they are both in the denominator of this quotient, both of them will get a minus when we separate this thing all the way out. So that's where I'm going to start. I'm going to use the product rule and the quotient rule to expand this thing. And then once it is expanded, I'll see if there's anything that can simplify further. To expand, remember every single piece has to get the log and the appropriate sign to separate. So I'm going to start with log base A of m squared. I use addition for the top, log base A n cubed. Subtraction for the bottom, log base A to the 3/4. Still subtraction because of the bottom, log base A of B to the 5/4. Now, each one of these has a power attached to it, which means that all of them are going to follow the power rule, and the power is going to drop to the bottom. This guy, the 2 drops down. 2 log base A of m plus power drops down. 3 log base A of n. This one follows a special rule, and it just so happens that the base of the log and the base of the exponent match. And remember, when that happens, all of it cancels, and the only thing that's left is the power. So this piece is only going to have a 3/4. And then minus power drops down to the front, 5/4 log base A of B. Nothing else follows any of those special rules or cancels out, so we are as simplified as possible. Now that's writing in expanded form and expanding these things out. In the next little set, instead of expanding things, we want to take things and smush them together. This is going to be helpful when we go to solve log equations, because when we solve logarithm equations, we want to make sure each side of our equation is in simplest form, and sometimes that's going to involve smashing some stuff together. So this time we're kind of working our way backwards. Any coefficients are going to pop up and become powers. Addition is going to become multiplication, and subtraction will become division. We're looking for those different pieces. Each one of these logs should have a single log in the front, and then everything else kind of rearranges itself around there. So, for example, in number 5, the first part has no coefficient, which means no power, but the second part has a coefficient of 2, so that's going to go up to the top, and this is going to look like log base 5 of x minus log base 5 of y squared. Now we have the same exact log here, matching, which is good. Subtraction in the middle, which should indicate that we are going to have a quotient. So that means we're going to have a single log, base 5, and it's going to be the first piece divided by the second piece. So x divided by y squared. A lot of people like to put parentheses around these expressions. It looks nicer with the parentheses just to show the log is here, the base is the 5, this is what we're taking the log of, so we put parentheses around it so there's no confusion. It is helpful to separate those like that. And so there we go. Now in this next one, we have a coefficient out in front of a binomial log expression. Before we can deal with this log expression and condensing it, we have to get that 1/5 distributed in to each one of these terms. When I distribute it in, it's going to become a coefficient on both of them. So that's going to look like 1/5 log base 7 of x squared minus 1/5 log base 7 of PQ. Now, once it becomes a coefficient to each part, remember, we're working backwards, so coefficients are going to go up to the top as powers attached to each one of these logs. So the 1/5 is going to come up here and up here, and it looks like log base 7 x squared to the 1/5 power minus log base 7 PQ to the 1/5 power. Now, these two parentheses having a power on the outside, it doesn't matter that that power is a fraction. It follows the same power rule as regular exponentials. So that means that I have to follow the power rule to simplify each one of these expressions. So get it in simplest form. The power rule says that the power on the outside gets multiplied by all of the powers on the inside of these parentheses. So log base 7, x to the 2 times 1/5 is x to the 2/5 minus log base 7. Each one of these has a power of 1, so 1 times 1/5 is 1/5. P to the 1/5, Q to the 1/5. Now we are undoing addition and subtraction in these problems. This problem has one piece minus another, which means we're going to turn this thing into a quotient. Single log base 7. The quotient will have x to the 2/5 on top. The minus sign creates the division bar. And on the bottom goes this whole other piece here, p to the 1/5, q to the 1/5. Now, it's important to note that when you have logs in this form and you have all these rational expressions, not rational expressions, rational exponents, and all the rational exponents have the same denominator. All of these have a denominator of 5. Typically, that will be written as a root. So it's probably a good idea to write this as a root unless Hawks says that you can leave it as an expression with rational exponents. This would be log base 7, and then it's a 5th root, because all of them again have a denominator of 5, and then they'll just keep their numerator as their power. So x squared on top, p to the 1st, q to the 1st on the bottom. So typically I'd say that yes, you will have to go this far where you're going to write these logarithms as a radical if it's necessary. But just pay attention to what Hawks says you're allowed to have as your answer, because if it says you can leave the rational exponents, then go ahead and leave them. So that one was pretty involved. Let's take a look at this next one here. This next one has 3 different pieces. All of them have a coefficient, which means all of them are going to end up having a power. pop all these powers up to the front, up to the top as exponents first. Log base A of x to the 1/2 plus log base A of y to the 4th minus log base A of x cubed. Now, this particular problem happens to have addition and subtraction in it, which just means that we are going to have a product and a quotient involved in our final answer. So we're going to go ahead and combine single log base A at the front. The product that goes on the top of the fraction bar is x to the 1/2, y to the 4th. The piece that goes on the bottom is the only part that's subtracted, which is the x cubed. Now, once we get in this form, I want to draw your attention to this quotient, because this quotient happens to have some like terms in it. You can see in the top there's an x with a power, and in the bottom there's an x with a power. When you have the same term on the top and the bottom raised to a different power, you can simplify that by subtracting those powers. So I'm going to come over here to the side because I have to do some fraction subtraction. So my x power is going to be 1/2 minus 3, which is 1/2 minus 3 over 1. And I need a common denominator, which is 2. So this is 1/2 minus 6 halves. Multiply top and bottom by 2. And that gives me negative 5 halves. So this looks like log base A, x to the negative 5 halves power, y to the 4th power. Now, it is probably not going to allow you to keep this as your final answer, I would assume. Typically, negative exponents are not considered simplest form. So I would bet that you're not going to be able to leave it like this. But there's a quick fix for negative exponents, and that's just to send them to the opposite side of a fraction bar. So if I take this entire x piece and put it down to the bottom, it's going to simplify this thing and make it a positive exponent. Y to the 4th over x to the 5 halves. Now, since the y doesn't have a denominator and the x does, I think you're going to be able to just leave it like this, because I don't feel like they have you write square root x to the 5th for just this part. Typically, it's like if the whole thing can be written as a radical. But if it wants your answer in terms of radicals, this bottom piece will just be the square root of x to the 5th. And you don't even have to put the square there. I just put it there so you could see where it went. But I don't think that's going to be necessary. All right, let's take a look at number 8. Number 8 also has quite a bit going on. First thing I notice about number 8 is that it has some rational expressions for these two variables. And for the beginning part of this, I'm not going to deal with them as fractions. I'm going to write both of them as expressions with a negative power, just to make it a little bit easier to look at. So I'm going to rewrite this thing as 2 log base A, no, not log base A, log of A squared B minus log of B to the negative 1, which I'm allowed to do just to make it look a little bit nicer for now. And then plus log of a to the negative 1. And now I have to go and move this stuff around. Now remember, when you're writing these things as a single log, you have to take any coefficients and pop them up as a power. It's probably a good idea if I put parentheses around this too. And maybe this one just for good form, just so it looks nice. Okay. It also makes it a little bit clearer because I'm going to take this and pop it up here as a power on the whole thing. And when we have log base, I keep saying base. There's no base this time. It's 10, so it's just a common log. Log of a squared b, the whole thing is squared, and that makes it a little bit more clear. Minus log of b negative 1 plus log of a negative 1. Now, the reason why it's probably a good idea to write that thing in parentheses, other than the fact that it just looks better with parentheses, is that this here becomes the power of a product, so we have to bring this power in to make this thing simplest form. So, log of a to the 2 times 2, which is a to the 4th, b to the 1 times 2, which is b squared, minus log of b negative 1 plus log of a negative 1. And now I can condense this thing down. Now I need to be very aware of my signs, because anything that's after the minus is going to go on the bottom, and anything after a plus is going to go on the top. Bottom, top. So single log, and we're going to have a fraction here. A to the 4th b squared is on the top. Also, this plus sign here means that a to the negative 1 is on top. B to the negative 1 goes on the bottom. And now we've got this hideous looking expression with A's and B's in it, all of which can be simplified in some way. First of all, I have a to the 4th and a to the negative 1 on the top in the same line. That means we're going to use the product rule, and the product rule says that when you have the same base and the operation is multiplication, you add the powers. So 4 plus negative 1 is a cubed. Similarly, we have a quotient involving b squared and b to the negative 1. Quotient rule says subtract. 2 minus negative 1 actually means 2 plus 1, so b also has a cube attached. And this is in simplest form. Everything is condensed as far as it can be. No addition and subtraction left. All the powers are simplified. So that is condensing. And actually, the condensing that we are going to do in section 5.5 is a much more simplified version of this condensing. It's not nearly as intense as it is in here. This section is really just to kind of apply all the different types of things you can do with these properties, and also bring in the exponential properties as well for extra practice. So let's see here. We've got the change of base formula. The change of base formula is the way that you evaluate logs using the calculator when you are not dealing with log base 10 or natural log. because it could be any log base 4 of 7, log base 19 of 0.2, whatever the case is. And there's no button on most calculators. I'm not going to say all of them. Some calculators do have a button where you can put in the base. But in that case, the calculator is just doing the formula for you. In our case, we're going to assume that we don't have that calculator, and therefore we need a formula to be able to do this. Now, the calculator is still going to do all of the work for you. You just have to make sure that you put it in correctly when you put it into the calculator. And what I mean by that is, when you're trying to take the log of any base at all, you want to take the common log of the big number and divide it by the common log of the base of the logarithm. When you type it into the calculator and you hit the log button, it automatically pops up a left parenthesis. You are going to fill the first number and close the parenthesis before you hit the division key and type in the second log. The second log will be log. Again, it pops up a parenthesis. You type in the base of the logarithm and close the parenthesis. It is very important to close the parentheses before you hit equals. That way, the calculator will do the appropriate order of operations. Because if it doesn't do the appropriate order, you will not get the correct answer every single time. So to practice change of base formula, we have an example here. And it's log base 5.3 of 1700. So the change of base formula says that we go into the calculator and we type in log 1700, close it, divided by log 5.3, close it, equals. Now, once you make sure that everything's closed off and hit equals, it is going to calculate it for you. You will round it to the appropriate decimal place. And in this one, it's the thousandths. So 3 decimal places would be 4.460. And you can apply this formula with any log. The only time this formula is not necessary is if you're actually doing just the common log or just a natural log. Now there's a little bit more evaluation practice here. And this is when we're evaluating logs without using a calculator, so that we either get integers or simplified fractions. And this is going to be possible when we have log bases and exponentials where you can use those special rules that they have. So, for example, the first one, log base 5 of 25 cubed. 25 can be rewritten using 5 as a base. So we could write this as log base 5 of 5 squared cubed. Now 5 squared cubed is not in simplest form. So in order to actually be able to handle this, we have to simplify it first. All we have to do is use the power rule that says we multiply the powers. And now it says log base 5 of 5 to the 6th. This one is one of those special rules, and we actually saw it quite a few times already, where the base of the log and the base of the exponent match. So they all cancel, and all you're left with is 6. The second one of these examples follows 2 different steps. There's 2 different special rules involved. And the first one comes from the rule about natural log and e. According to the rule, when you have the natural log of e to a power, the natural log and the e cancel each other out. And when that happens, you're just left with the exponent, which in this case is 1.5. In the second one, not equals, should say minus log base 4, 2 can actually be written as 4 to a power. You have to kind of think outside the box here because 2 is not 4 to an integer power, it's the square root of 4. And instead of writing it as the square root of 4, we can write it as 4 to the 1/2 power. Remember, radicals and rational exponents are interchangeable. And now it falls under that nice little rule where we can cancel the log, the base, and the base of the exponent, leaving me just with the power. So this looks like 1.5 minus 0.5, which is very easy math. 1.5 minus 0.5 is just 1. So if you have to rewrite, most of the time I know we talked about it before, how you take bigger numbers and make them smaller. If you absolutely have to take a smaller number and make it bigger, you can use fractional exponents. It's just a lot of times people have a hard time using fractional exponents. But if you're comfortable with them, great. So those are just some special ones. The last little part of this is applications. And applications are going to involve some of these special little formulas. So we've got here the pH formula. pH is just negative log H3O, I guess that's positive, or H3O plus. And then it tells you what that is, the concentration of hydronium ions. That's typically given to you. Then we've got the Richter scale, that's earthquake measurement. It's right here. Richter scale also involves log, but it's the log of I over I sub 0. Now, those are also given. I sub 0 is the intensity of an earthquake right as soon as you can actually measure one. So the first possible like inkling of an earthquake. And then I is the intensity of the current earthquake that you're trying to analyze. Then we have the decibels. That's for measuring sound. The decibel formula looks very similar to the earthquake formula. This one has a leading 10, so it's 10 times the log of I over I sub 0. And this time, I sub 0 is the intensity of a sound as soon as you can hear it, as soon as it makes a sound. And then I by itself is the intensity or how loud the sound is that's actually being analyzed. So those are just some formulas. And we've got a few examples involving each one of these. So let's take a look. First one is talking about tomato juice and pH. So we're going to be using the pH formula. And in this example, they tell us what the concentration is. So here's our concentration. And that's really the only measurement that's involved in our formula. If we're trying to find the pH, we're going to use negative log of this value, the H3O positive or H3O plus, which is 3.16 times 10 to the negative 6 power. Now, you're welcome to split this thing up and use the addition, which is the expansion property. Instead of doing that, I changed this thing to a decimal and then just plugged it into the calculator. It doesn't matter which way you do it. 10 to the negative 6 power means you take the decimal and move it 6 places to the left. 1, 2, 3, 4, 5, 6. So it does end up being a very small decimal. Negative log point 1, 2, 3, 4, 5 zeros, 316. But if you do it that way, the calculator does the work for you, and then you don't have to spend the time expanding it out. So I just felt like it was faster to change it. Your call. But if you plug in negative log of this really small number, it gives you the final answer, which is 5.5. And so the calculator does the work for you. These last two involve the other two formulas. Number 2 is the Richter scale. So it says the 1994 Northridge, California earthquake measured 6.7 on the Richter scale. That is the R value. That was what its measurement was. It's asking what is the intensity if you are relating this to a 0 level earthquake. Now the formula for this is a little bit different than what the formula is given in the notes. You're relating the intensity I to the intensity of this 0 level earthquake. And we know the R value instead of going to find the R value. So these are the two pieces that we're using variables for. And we have to use the same variable for both of them in order for this to work. So we're going to set this up as R equals, so 6.7 equals log. On top is supposed to go the intensity. We are measuring the intensity relative to a 0 level earthquake. So what we're going to do is use a 0 level earthquake as the base and then multiply it times x as our variable relating it to a 0 level. The intensity would be the 0 level times whatever this would be, would give us our new intensity. And it's over I sub 0. So we kind of had to redefine I based on this little tiny bit of information. Now, another reason why this is nice is because since we have the same variable in the top and bottom of this fraction, it cancels out. And now it looks like this. Now we have to get a little bit creative here. And we have to think about how we're going to actually be able to solve this. So what I did here was rewrite this as an exponential equation. And when you have a single log on one side and a number on the other, that's best practice. In order to rewrite this as an exponential equation, we need to know what the base of the log is. We did some log conversions before where we converted logs to exponentials and exponentials to logs. Now we're actually applying it here, but we have to have a base to do it. So remember, when you're dealing with common logs, the base is 10. And now we can do a conversion, changing this log expression, or log equation rather, into an exponential equation. Remember, when you're dealing with exponentials, the log drops off and you use the base of the log as the base of your exponential. The number by itself on the other side becomes the exponent attached to your base. And whatever was attached to your log base detaches and goes over on the side by itself. And now we have an exponential equation, 10 raised to the 6.7 power. And the calculator is going to do that math for you as well. It's a big number. It says 5011,872 point, I went to 2 decimal places, 34. Just make sure you round to whatever decimal place they tell you to. It doesn't say, so I just did 2. So this one was a little bit tricky because of how the equation had to be written. Hopefully going forward, these will be more straightforward. All right, last one here deals with the decibel scale. And the decibel scale is similar to this one. It has a 10 in front, but it's the decibels equal 10 times the log, and then it's intensity over the initial intensity. This time they give you the intensity and they give you I sub 0. So this is going to be a little bit nicer for us because it's straightforward plugging in. We're looking for the decibels, so this time D is the variable. And it's 10 times the log of I, which is this value here, 2.19 times 10 to the negative 11, divided by this value here, 10 to the negative 12. Now, I know it's hard to maybe see this right off the bat, but this thing can be simplified because it has these like terms involved in the quotient. Remember, when you have the same base raised to different powers in a quotient, you can simplify those by subtracting the exponents. 10 to the negative 11 minus negative 12 actually means 10 to the 11 plus 12, which is the first power. And this here actually isn't a terrible looking decimal. 10 to the first power means you move one place to the right. So we're trying to find what is 10 times the log of 21.9. And you can put this whole thing into the calculator. 10 times log 21.9. And it's going to spit out that final answer for you. This time, for whatever reason, I rounded to 3 decimal places, and I got 13.404. So these are just a couple applications of the different log equations. And then all of these log properties, which we're going to see again, some of them at least in section 5.5. So they will be helpful in the future for condensing so that we can actually solve. So I hope this helped. I hope that the word problems that pop up into Hawks aren't too terrible for you. And I'm sure that you guys will be great. And if you are having any issues, remember to seek out tutoring from any of the available instructors on any campus close to you. Tutoring schedule is found in the end of the syllabus. So take care, and I will see you guys again soon. Well, I guess you'll hear me again soon in the video for section 5.5. So have a good one.